We can read the pictures, and every equation is tamed into a state and its rates. Now, at last, we compute, and the method that powers nearly every simulation you have ever seen is almost embarrassing. Stand at your starting point and ask the equation for its arrow. Take a small step along that arrow. Ask again from where you landed, step again. That is the whole method. It is called Euler's method, and a person who has never heard the words differential equation could carry it out with a pencil.
But the arrow is only right where I asked. By the end of the step, the true path has curved away.
It has, and you can see the gap. The straight steps cut corners the curve does not. So shrink the step. Half the size and the corners get gentler. Half again, and the broken line starts hugging the curve. Watch the numerical path chase the true one as the step shrinks. That chase is the whole subject of numerical differential equations. Now put Euler to work on our warm-up system, the spring in its tamed form. 2 numbers, position, and velocity, both nudged at every step. The spring lets us check, because the true answer is the closed ellipse from the first episode. Around and around, the same loop forever. Here is Euler's version, laid on top of it. It does not close. Every lap sits a little outside the last, a slow spiral outward. Our simulated spring is swinging harder and harder, gaining energy from nowhere.
Where is the energy coming from?
From the corners. Each straight step leaves the curve on the outside by a whisker. But the errors do not average away. Lap after lap, whisker on whisker, they compound always outward. A smaller step spirals more slowly, but it still spirals. Remember this picture. It is not the end of the story, and fixing it properly is an episode of its own. Euler's mistake is trusting one arrow for the whole step. The fix is to peek ahead. Take a trial half step, read the arrow out there in the middle, then come back and take the real step using that midpoint arrow instead. One extra glance, and the step tilts to match how the curve is bending. Push the same idea to 4 well-chosen glances per step, and you get the classic workhorse, Rungakuta, the default solver in nearly every library. Same spring, same size of step, new stepper. The wild spiral collapses onto the ellipse.
4 glances per step sounds expensive.
Here is the fair comparison. Give Euler 4 steps, each a quarter of the size, so both methods ask the equation 4 times. Same price, Euler still spirals, Rungakuta hugs the loop. Being clever about where you look beats simply looking more often. One scene of code for the entire series, because this method deserves to be seen whole. Here is Rungakuta, the workhorse in 6 lines. Look at what it does. 4 times it asks the rules for the rates, once at the start, twice at trial midpoints, once at a trial end. Then one weighted average, and the step is taken. That is the entire method, no theory on the screen, 4 questions and a careful average. Now the part that should feel like a magic trick. Nothing in those 6 lines knows what is being simulated, or what order the original equation was. All of that lives in the little rates function beside it. For the spring, the rates function is 3 lines. Unpack the pair, return the 2 rates. Swap it for the pendulums, and the stepper does not change by a single character.
So the solver is generic and the physics is a plugin.
Exactly. And later in the series, the state will grow. 4 numbers for a double pendulum, 40 for a rod full of heat. And these same 6 lines will carry them all. We will never edit them again. Real solvers add one more courtesy. They do not use the same step everywhere. Where the curve runs straight, long strides are safe, so they stride. Where it bends hard, they slow down and tiptoe. Watch the footsteps along this path, sparse on the straightaways, crowding together around the sharp turn. The solver estimates its own error as it goes and spends effort only where the problem demands it. That is what is really running when you call a library. One honest warning before we cash in. Some systems mix a very fast motion with a very slow one, and they are called stiff. Feed a stiff system to our steppers, and the fast part explodes the step unless you make it absurdly tiny, paying millions of steps to watch the slow part crawl. There is a family of solvers built for exactly this, implicit methods, and knowing that name is enough for now. If your simulation blows up for no visible reason, suspect stiffness first. Now the payoff. The pendulum has no formula, no exact ellipse to lay under our path, no answer key at the back of the book. This is why we drilled on the spring first. We tested the stepper where the truth was known, and it earned our trust. So we point Rungakuta at the pendulum and press play. The stepper neither knows nor cares that the equation is famous for being unsolvable. It just keeps asking for arrows. And the paths it draws land exactly on the portrait we read in episode 1. Closed loops inside the eye, wraparound curves above it. The picture told us what kinds of motion exist. The stepper tells us where the pendulum will be 7.3 seconds from now.
So the graphical view and the computational view are partners, not rivals.
Exactly. One shows the whole landscape, the other walks a chosen road through it. Next time we ask a sharper question, out of all these possible roads, which one is yours?